Okay. So what's the payoff here? Well, this is derivative with respect to y, so, and actually I should have written this as a partial derivative, because that slope is still a function of two variables, okay?
Is the partial f with respect to x function of two variables?
I got my x's.
Okay.
Yeah, I look, okay. If I'm following this logic, I've got them backwards, but it's okay, because fxy is the same as fyx, as you've encountered, I'm sure. It's on the problems I say. You're aware of that, right? Oh, geez, I was pretty sure I'd assigned problems that addressed that, but yeah, I don't remember seeing them in your homework, so maybe I didn't. Anyhow, that's true. Okay? And all you gotta do is take some derivatives and see. But also, we're gonna go back like a week from today and prove a lot of this stuff.
What does fxy mean?
Means the derivative of f with respect to x, the derivative of that with respect to y.
Okay.
Mixed partial. And fyx means take the derivative with respect to x of the derivative with respect to y. Okay? It just means this.
Okay.
We can do that. And let's actually go ahead and do that for our famous discriminant of the quadratic function. Okay? But first, let's see that what we're looking at here is the derivative, a mixed partial, that tells you how these slopes change, okay? Okay, because again, you're looking at a slope that's a partial with respect to y, and you're looking at how that changes with respect to x, right? Okay, so it makes a certain amount of intuitive sense, and as I say, this is a really important picture. It's
So
underlies some of the toughest stuff we do.
What does this represent in our picture?
It represents how much these slopes differ divided by your x interval. So it's like the change in your y slope divided by your change in x. And we can do that with epsilons and deltas, and we will. But the use of it will be fairly intuitive. Now what we're really on is chain rules, right? Since this picture came up, and since I was going to talk about this anyway, I talked about it a little bit in advance because that's the way the conversation went. But let's come back to the chain rule, okay? And this isn't really an application of the chain rule at this point. I used the picture again to illustrate how whatever change in y is driven by your change in t, okay, determines how much your function will change when t changes. At least how much it changes in this direction, okay? And then, similarly, whatever your x function is, change in t causes x to change by a certain amount, which then tells you how much the function changes in this direction. And of course, you add these two changes for the reason that's very obvious, because this is practically a parallel a rectangular prism truncated, or rectangular parallel pipette truncated by a plane. Plane being your tangent plane. Again, your tangent plane isn't quite a plane because these slopes aren't equal, but in the limit, the difference becomes insignificant. Okay. So this is the change here. And let's just color code it, okay? Let's find a good color. I don't know what happened to my yellow. I had a big piece of yellow chalk yesterday. I used it about twice. Okay? See, that's this. Okay? Where your X change is dx dt times delta t. Okay? And your delta y is dy dt delta t. Now that's what I was talking about when I said your change in t causes a change in y. This is the rate at which y changes with respect to t. You multiply that by the change in t, you get your change in y. And similarly with x. Okay? So you're going to get df, dy, dt. Why is that? That's because this change here is just fx delta x. Fx is your slope, delta x is your interval. That's how much your slope changes, right? And this change is fy delta y. So when you come all the way around here, if I can do this without totally messing up the picture, what you end up with is a slope here being pretty much the same as slope here, or the slope from here to here the same. You end up with this plus this. Okay? And here we can then say that this change is approximately fx delta x plus fy delta y, which equals fx times delta x being dx dt delta t, right? Hope I'm getting this from camera, yeah. And fy times dy dt delta t. And this is, you know, approximate to the extent that your intervals are all small, right? So you got a little tiny infinitesimal change in t, right? Which causes little tiny changes in x and y, which in turn causes changes in the value of f. If delta t is little tiny enough, and x and t are both differentiable and all that stuff, right? Then in the limit, this expression gives you this expression. Okay? Well, this expression divided by delta t approaches this expression, right? So I guess I could even say Okay, I factored out my delta t because I didn't have room to write it in twice, okay? We're taking the limit of this over delta t. I guess I gotta close a parenthesis out here somewhere. Well, delta t's drop out, you get fx dx dt plus fy dy dt, which is this. That's not a rigorous proof. I didn't run it through all the epsilons and deltas and stuff, okay? And the whole limiting process, but you just write out the details, and details are not that difficult. Okay? So we'll do that. Okay. So, I hope we've made this believable, because we're going to pull the stops out and do a bigger one, where x and y are functions of two variables.